You are welcome to the GMAETS 41 live stream class on physics. Because this particular class is dedicated to our scholars in high school, senior high school, senior secondary school, SS1 to SS3. However, like I rightly mentioned in the morning when I had advanced maths class with those, undergraduate students, those in 100 level, I explained that it's important you guys tune in because it's possible that what you see being treated might be something that you need. And to the best of my knowledge, I am aware that 100 level students, they treat the concept of magnetic field. If not for anything, for my friends in Unizik, this semester in your Physics 102, one of the topics you're going to study there is magnetic field. You're welcome to join the class. As soon as you join the class, you know what to do. Give this live stream class thumbs up and quickly share the link to your friends. Invite them to join the class right away. We shall be looking at the concept of magnetic field briefly, within the limit of time that we have. And of course, we will be getting to learn some things about magnetic field, including flux, what is called magnetic flux. We're also going to give attention to the concept of magnetic force that is acting on a charge moving in a magnetic field. We're also going to give attention to the magnetic force acting on a current carrying conductor. That is a conductor that is carrying current and then placed in a magnetic field. We shall also give attention to how to determine the force on such conductor. Trying to share information. All right. So without wasting time, we shall define the term magnetic field. We shall define the term magnetic field. Magnetic field is defined as a region around a magnet where the force of the magnet is felt. A region around the magnet where the force of the magnet is felt. That field is created by the magnet itself. I'm going to show you something, okay? Here I've got my magnet. This is a magnet. This is a magnet. Is that okay? Now this magnet, as I'm holding it like this, it has created a region. It has created a space around it where the effect of this magnet can be felt, where the force of this magnet can be experienced. Is that okay? So the region around this magnet where the magnetic force is experienced is what we call magnetic field. Just like you have a football field. If you are in a football field and there are players in the field playing soccer, you will feel the force of the players. Imagine that the ball gets close to you. Some players might just run and hit you. You feel their force. But if you are outside the field, you won't feel the force. No player is going to come hit you. So in magnetic field, the region around the field where the force of the magnet is experienced is what we call magnetic field. Now, like I said, magnetic field is created by what? By a magnet. You want to take note of that. If you have a magnetic field, if a field is created by a magnet, any magnetic substance per se that approaches, that enters that field, will experience the force of the magnet. Now, I've got this. I have this. Okay? I have this. I'm going to hold it here. Let me hold this magnet at this point. Let me hold this magnet this way. Then I want to do something. Just observe. I'll be bringing this metal close to the magnet. You know, from here, nothing is happening. Nothing is happening, you know. This is just free. It's free, nothing is happening. No force is experienced by this metal. It simply means that the metal is not in the magnetic field. It's not. Now let's be going close. Let's be going close. My right hand here, I'm holding a magnet, a bar magnet. And my left hand, I'm holding a metal. There is no effect felt here. No force is experienced by this metal. If I leave this metal, it will fall down. Just watch. You see? Because the metal has not entered the field of the magnet. Now we shall be moving close. We shall be moving close, approaching. I'm feeling something on my hand now. It's as if something is trying to pull this my left hand. I'll be approaching it again. I'll be approaching. Let's see what will happen once the metal enters the magnetic field. Just keep watching. Did you notice that? Without making any contact, this metal was dragged, was attracted. It's like a force held the metal and pulled it to the magnet. Watch again. You can see there is space between them. You notice what it did? This metal was attracted by the magnet, felt the force of the magnet because the metal has entered the field of the magnet. If I leave the metal this way as it is falling, you notice, as it is falling, it's falling into the magnetic field, and hence it will be attracted. It will feel that force. So that is the concept of magnetic field. Region around the magnet where the force of the magnet is being experienced. Now, when this metal entered the magnetic field without contact, a force attracted that metal, thereby sticking the metal to the magnet. It is just like somebody holding, this marker with a force and then dragging. So there is an invisible force there which exists, the magnetic force. Now, I've just said that it is as if something held the metal and pulled it towards the magnet. We can actually represent that thing that held the metal per se and attracted and dragged it to the magnet. We can represent that thing with what we call line of forces. Magnetic line of forces. We can represent them with magnetic line of forces. And so one can see in the study of magnetic field, if I have a magnet here, you can see the line of forces. These line of forces are imaginary. Imaginary because there is no such line being drawn. We imagine that because of what happened, you can see how that metal was attracted, was dragged to the magnet. It is as if there is a line pulling it with a force. So magnetic line of forces are imaginary lines of force where a magnet might take its direction if it is free to move. The direction where a bar magnet will take if allowed, if free to move in the field. That is what we call magnetic line of force. Now, this magnetic line of forces, which I say they are imaginary, we can sketch it this way. And that will now bring in the concept of the poles of a magnet. A magnet is said to be dipole. A magnet is said to be what? Dipole. Because it has two poles, the north and the south pole. All the things I explained about, the definition of magnetic field, please, you have to make a note of it. You have to make a note of it. I won't be copying all those notes here. Is that okay? So let us assume that I have this. I'm using it to represent a bar magnet. And then, okay, let's say I have something like this and I shade this part. Must I shade? It's not necessary. Let me call here North Pole. Let me call here North Pole. And then I'll call here South Pole. A magnet has North and South Pole. So I have this again. Let's have another magnet here. And then I decide to also create the poles there. Let's say this is North and this is South. So a magnet is said to be dipole. Two poles, because it has North and South poles. The South pole behaves as negative terminal, while the North pole behaves as positive terminal. The North pole behaves as positive and the South pole behaves as what? Negative. You know, under electricity, electric field, you study electricity, you have charges, positive and negative charge or charges. Positive and negative charges. In the same way that electricity is dipole because you have positive and negative charge, in magnetic field, magnet is also dipole because it has two poles, North and South. North behaves as positive, while South behaves as what? Negative. So if I am to draw the line of force, let me pick a North pole of a magnet. Assume that this is North pole of a magnet. What will the magnetic line of force look like? Those imaginary line of forces, which I talked about earlier, what will it look like for a North pole of a magnet? This is how the imaginary lines will be traced. You have something like this. Now let's say something of this kind. And then, because this is the North pole, I told you that the North pole behaves as positive. So the line of force will be moving away from the North pole. They'll be moving away from the North pole. Something like this. This is the magnetic line of force of a North pole of a magnet. If it is South pole, this is what you're going to see. Let's take this to the South pole. The lines of forces of the South pole goes like this. It is the direction of the line of force that we are interested in, the direction. This one, the line of forces in North pole, they move away from the North pole. But for the South pole, they converge. They move towards the South pole. Which means that magnetic line of forces generally rise from the north and then terminate at the South pole. Magnetic line of forces, they rise from where I said North pole and they terminate at the South pole. Very important point to take note of. Magnetic line of forces, they rise from the north and terminate where? The south. Because the north behaves as positive terminal. And under electricity, positive charges, if you are drawing electric line of forces, for positive charge, the line of forces will diverge, move away from positive charge. The same thing here, north represents positive. The line of forces will diverge, will move away from it. Welcome to the class. Anurag, nice explanation. Okay, thank you very much, I appreciate that. Please, as you join the class, I will appreciate it even more if you share the links to friends, to classmates, okay, whom you know are offering physics. They would need it. Okay, let us move on. Having explained this issue of magnetic line of forces, I want to tell you something about flux. Flux, F-L-U-X. Flux is defined as collection of line of forces. Under electricity, that is electric field, we have electric line of force. In magnetic field, we also have magnetic line of force. The collection of magnetic line of force is called flux. Flux or magnetic flux. Magnetic flux. We use this symbol for it. Magnetic flux is a collection of magnetic line of forces. Magnetic line of forces. Okay, magnetic line of force. Look at all these lines. Put together, they give us what we call flux. The unit of flux is Weber. Note, the unit of flux is Weber. Unit of flux is what? Weber. We are moving on. Shall Earth act as magnet? Yes, it acts as magnet. However, this class today will not cover it. Are you getting me right? Make sure you follow up with our classes, subscribe to this channel if you have not yet done so, and turn on the notification bell so that once I kick off any class, you will be personally notified. Take note, we have a timetable, our online class schedule, and we stick to it. We just kicked that off this week, that timetable. So follow through in the post section of this channel. You will see that timetable. Are you getting me right? You see that timetable, so you know when we have classes. Okay, we are moving on. I've talked about the concept of flux. Let us now talk about magnetic line of forces for like poles and for unlike poles. You know, because a magnet is dipole, it has two poles, north and south. We can experience attraction in a magnetic field and we can experience repulsion in a magnetic field. Like we know about the fundamental law of charges. Like charges, they repel. And unlike charges, that is opposite charges or opposite poles, they attract. Magnetic field is a field where we experience force of attraction as well as force of repulsion. I remember under gravitational field last semester, just a few months ago, I taught the concept of gravitational field, and I explained that in gravitational field, the force we experience there is only force of attraction. In magnetic field, we experience both force of attraction and force of repulsion. The same thing in electric field. So we want to study the magnetic line of forces when you have two like poles and when you have two unlike poles. But I'd like us to demonstrate something. Let's see if I can reach out for my second magnet here. There is something that you may have noticed. If you've played with a magnet before, I've got two magnets here. These are two magnets. There is how I will position these two magnets, they will attract. In this position, there is no attraction. I'm feeling repulsion now. Okay, let me turn this one. You see, in this position, if I bring this thing close, they will attract. Did you notice that? So you notice that the line of force is as if there is an intersection. They pulled towards each other and they intersected. Oh my gosh. And they intersected. All right? The magnet has fallen. So, once again, watch. And this force acts from a distance. You notice how one flew to the other magnet. So that is attraction. It shows that these two poles I am holding, one is north, the other is south. Watch again. Good. Now, if I turn this, if I turn the other way around, please try to observe what might be happening. I'm trying to force them together. I'm trying to force them. You notice this distance is sufficient for them to attract if the two poles were to be unlike poles. But look at what is happening. If I tell you the way my fingers, right, are struggling here, you can try this at home. So this shows that these two magnets, the poles facing each other, are like poles. Maybe north-north and south-south. So there is no attraction. Rather, there is repulsion here. This means pulling my hand. It's pulling them away. This simply shows that the line of force, the magnetic line of force, which we say it is imaginary because we are not seeing any line here, but it appears as if something is pushing the other. So when the line of force comes out from this one comes out, they approach each other and they say, no, we are not meant to be. So they diverge, they push each other away. I am going to sketch this thing on the board for you to watch. Please observe. Let me use this part. Or should I wipe this and, okay? I'm going to use this part. Let me manage it. I'm going to draw the flux pattern for unlike poles first. Flux pattern. That's what we refer to it. For unlike poles. Unlike poles. So maybe I have north and south. Let me say that this is north. Let me say this is north pole. And then let me say this is south. South pole. Here will be north. Here will be south. Now, these two poles are facing each other. The two poles, north and south, they are unlike. When I demonstrated this, you notice that when we had unlike poles, north-south, there was an attraction. The line of forces came out and then merged. So this is what we are going to get. The line of force will come from this north, link up to the south. You know, it's as if as the line of force of the north is coming out, the line of force of the south is coming, and then they attract. We have something like this. We have this. We have this. Then we could move up, move this way. Let me wipe off this south and north here. It's not necessary. So this is how the line of force is going to be for the case of two unlike poles. Two unlike poles. This is the flux pattern. This is the magnetic line of force pattern. Remember, flux, line of force is collected. Okay? This is interesting. This is interesting. Let us look at the flux pattern. Flux pattern for two like poles. Must I write two like poles? Let's just say like poles. Like poles. So I shall be using, let's say, north-north, right? Or let me use south-south, because I want you to see something. If you observe the way I showed this arrow pointing is very important. Please take note. If you observe these, the lines, I represented the arrow in such a way that it is pointing away from north and then converging to south. That was what I told you here. That for north pole, the line of forces diverge. They move away from the north pole. And then that of the south pole, they converge. They come towards the south. So in this case of north and south, the arrow is going to be shown in such a way that it comes from the north facing the south. Take note of that. Let us look at this. This time around, I want to use south-south. So I said that I have something like this. South. This one too. South. When I demonstrated this with my bar magnet, you notice that something happened. When I had like poles come together, they could not attract. Rather, I was feeling this repulsion, something trying to pull my hands, apart. This is how we show it. The line of force will come from here. This will come from here. Then as they are coming towards each other, of course, they will now repel. So there's going to be a kind of pushing away. This is what is going to happen. Watch. Something of this kind. Something of this kind. And then the arrow is going to be shown this way. The arrow is going to be shown this way. I told you that the flux pattern for south converge towards south. So we have something like this again. We have something this way. This way, this way, this way, this way. The arrow will be drawn in such a way that it will converge towards the south. Because for South Pole, line of forces converge to it. I hope this has not cut off. Okay, it's in line. Now, you notice that there is something here. The middle point, where it seems like no line of force crossed. As a matter of fact, not that it seems. That is the truth. There is no line of force that crossed it. Watch as I do this once again. You notice between them, there is no attraction. This is the same pole, either south-south or north-north. No attraction. In between, you notice that there is a free space there. That free space is called the neutral point. So the middle here is called what? The neutral point. The neutral point. Take note. Neutral point is defined as a point where line of forces do not cross. Neutral point. Neutral point. A point where line of forces do not cross. Please, dear friends, for more information about flux pattern, in the description section or description box of this particular live class, I have the link that will guide you to the GMAETS 41's full lecture on magnetic field. Reach out for the link, click the link, and then take the full lecture. You'll see the flux pattern for different charge configuration or different pole configuration. I'm saying this because you see, like this one I drew here is actually flux pattern for like poles which are equal. So I can say for equal like poles, for two equal like poles. I must not write it on the board, I'm saying it. This is flux pattern for two equal like poles. That is why the neutral point is at the center, the middle. If these are unequal like poles, let's assume that this south, the value of this, the magnetic field of this particular one is greater than the magnetic field of this particular one. The line of force of this bigger one will push towards the smaller one, so that this neutral point will now shift towards the smaller one, making the neutral point no longer to be at the center. Do you get that right? So you can learn more about it as we move on to the next thing of importance. I've explained this concept and shown you the concept of neutral point. This is the flux pattern for two unlike poles. This is the flux pattern for two like poles. Here there is attraction, here there is repulsion. And in the case of repulsion, you have a neutral point. Neutral point is a point where line of force do not cross. At this point, we are going to look at another concept now. The concept of force, magnetic force acting on a charge moving in the magnetic field. Please, you can screenshot what you have there on the board so that I'll wipe the board and then we move on. we are going to look at the magnetic force on the charge. I'm going to give you the formula of the magnetic force on a charge moving in a magnetic field. I'll give you the formula of the magnetic force on a current carrying conductor in a magnetic field. That is a conductor that carries current and it is moving in a magnetic field. I'll give you the formula for that. I'll also give you the formula that connects the magnetic field strength called magnetic flux density. We use B to represent it. I'll give you a formula relating it to magnetic flux. Further, let me just write notes. Magnetic field strength. Magnetic field strength. Field strength. Just like in electric field, we have electric field intensity. Magnetic field strength, also known as magnetic flux density. Magnetic flux density. Flux density. I think we can also call it magnetic induction. The symbol is B. Determines the strength. Determines the strength. Determines the strength of the magnetic field. Determines the strength of the magnetic field. So you take note of that. Okay? Take note of that. And when you are talking about the magnetic field strength or magnetic flux density, which we use B to represent it, there's a relationship between it and magnetic flux. The unit of magnetic flux density, the unit of B is Tesla or Weber per square meter. That's the unit of magnetic flux density or magnetic field strength. Are you following? Or simply you can call it magnetic induction. From this unit, that magnetic flux density has the unit Tesla, and that unit Tesla is Weber per square meter. Look at Weber per square meter. Per. Mathematically, we use division for it as a mathematical sign. Weber is the unit of magnetic flux. I talked about that earlier. Square meter is the unit of area. Is the unit of area. Therefore, we can say that magnetic flux density B is equal to Weber divided by square meter. Weber is unit of flux, magnetic flux. Square meter is unit of area. So if I have this, let's say that this is the surface placed in a magnetic field, and then let's say that this is the magnetic field, the lines of force. The lines of force. Are you following, right? And they are moving this way, crossing this surface. They are moving this way because this material of surface area, it has a surface area, you can see that, is placed in the magnetic field. This line of forces can cross that material. They can pass through. And as they are passing through, we check the area of the material, okay, that this magnetic line of force, this flux, the area they are passing through. And that now brings us to this relationship, that magnetic field strength, magnetic flux density, magnetic induction B is equal to flux, magnetic flux, unit Weber, divided by the area of the surface that is immersed in the magnetic field over which the lines of forces are crossing. Take note of this equation. This is our first equation, equation 1. B, you know the meaning already. This is flux. The unit is Weber. Let me just define A for you, where A is equal to area of surface. Immersed in the field, over which the flux lines are crossing, over which the magnetic line of forces are crossing. So take note of that, please. J preparation going strong. That's good. You're welcome, Zygon or Zygon. Please, you can assist me with the correct pronunciation. Okay. Welcome to join this class. You can tell us where you are streaming from, where you are learning from. Okay, that would be appreciated. If you connect to the class and you are not from Nigeria, you can indicate. Even if you are from Nigeria, you can tell us the state you are connecting from. Okay, now let us talk about the magnetic force on a charge moving in a magnetic field. Having established these concepts, magnetic force on a charge Q moving in the field of strength B and velocity, or with a velocity V. So we want to find the value of the magnetic force F that is acting on a charge placed in a magnetic field, and the magnetic field strength is B, as I explained here. Now the charge is moving with a velocity V. Charge, we use Q for it. So it's as if you have this magnet creating a magnetic field, and then there is a charge moving in it. The charge, as it's moving, it has velocity. The field has its strength, and that charge must feel the field, must feel the strength of the field. So what is the formula for calculating the magnetic force? In this case, the magnetic force F is equal to QVB. I can say at an angle, let me indicate, at an angle theta. At an angle theta to the field. So it is given as F equal to QVB sine theta. So you are expected to memorize this, equation 2. QVB sine theta, just a simple formula, right? Straight on like that. So you know the value of the charge, you know the value of the velocity, you know the value of the field strength. And maybe if you know the angle at which the field, at which the charge is moving through the field, right? Following, right? You use it, sine theta. Now, it's important for you to know at what point is the force acting on the charge maximum. At what point is the force acting on the charge maximum? It's important for you to know that. So you want to note this. If theta is equal to 90 degrees, the implication is that sine theta will be equal to 1. And F will now be equal to QVB. Permit me to write it F max. That F max means maximum force. So if you are asked, under what condition will a charge experience the maximum force or the maximum magnetic force on it? That is, if the charge moves at an angle of 90 degrees to the field, perpendicular to the field. Let me assume that this is the charge, and then this is the magnetic lines of forces. This is the charge. So if the charge moves perpendicular to the direction of the field at 90 degrees, the charge will experience the greatest force, the maximum force. Take note of that. And when do you expect it to experience the minimum force? Minimum force is when F is equal to 0. Are you following, right? When F is equal to 0, that is minimum force. And that happens if theta is equal to 0. Let me indicate it. Let's call this 2A. Equation 2A from here. If theta is equal to 0 degrees, sine theta will be equal to 0, and F will be minimum. That's the least force, because the force will be equal to 0. You know why? Fix 0 here. You have sine 0, which is 0. 0 times QVB will give you 0. And that is the least force. For the angle theta, for the charge to move at an angle of 0 degrees, means that the charge is moving in the same direction as the field. The charge is moving parallel to the field. Watch once again. If the magnetic field is going this way, and the charge, instead of moving at 90 degrees, is now moving this way also, the same direction. You know, parallel lines, the angle between them is 0 degrees. So if the charge moves parallel, moves in the same direction as the field, then the charge will not experience any force. In that case, we say the force is minimum, 0 degree. I hope you get that right. For that of 90 degrees, it is perpendicular. Okay, so take note of this. Screenshot what you have on the board so that I'll wipe it. And then we look at the next equation, equation 3. We have gotten 2 equations based on what we want to cover in today's class. So I hope you screenshotted this note on the board because I'm going to wipe it now. The unit of force has not changed. It has not changed. So I want to assume you know the unit of force. So if you used to know it as Newton, it still remains Newton. Now let us talk about magnetic force on a current carrying conductor. Current carrying conductor. Of length L. So the meaning of the term current carrying conductor means a conductor that carries current, that is, current is flowing through it in a magnetic field. So if you have a conductor and current is flowing through it, and you place that conductor in a magnetic field, the length of the conductor being L, the force that conductor will experience is given as F equal to BIL sine theta. BIL sine theta, equation 3. Where I is the current. The current in the conductor, then L is the length. It's already here, so I don't need to define it anymore. And you know the unit of these quantities. Current is in ampere, length is in the unit of meter. Please, once you join the class, give this class thumbs up and share the lessons to your friends. Share the link to this lesson to your friends so that they can join and also benefit from the class. Remember, you can become a channel member so as to follow through with what happens in GMAETS 41 fully. Join us on the platinum level. That will also allow you to support this channel so you continue to get the best. And once you become a channel member, you get even much more benefit. You get access to all members only video. There are some key videos that are meant for members only. So become a channel member on platinum level or diamond level. I will appreciate that. It's a means of supporting me as I continue to do the best for you friends. There are many other benefits apart from the members only video, you know, for being a member of GMAETS 41. Okay, I think the same thing, if theta is equal to 90 degrees, maximum force will be experienced. If theta is equal to 0 degrees, minimum force, the least force will be experienced. Okay, don't forget B is your magnetic field strength or magnetic flux density or simply magnetic induction. We shall pick just a few questions and then we would be done with the class. Our first question. Mind you that in each class we have what we want to cover. Okay? So we don't want to go beyond that, at least for now. All right, so we have this question. Find the magnetic force experienced by an electron. Find the magnetic force experienced by an electron of charge 1.6 times 10 to the power of minus 19 coulomb, projected into a magnetic field of flux density, projected into a magnetic field of flux density 10 Tesla, 10 T, with a velocity of 3 times 10 to the power of 7 meters per second in the direction okay, now A, parallel to the field, B, at right angle to the field, C, at 30 degrees to the field. A, parallel to the field, B, at right angle to the field, at right angle to the field, and C, at 30 degrees to the field, at 30 degrees to the field. Support from Russia, thank you very much. Support from USB, thank you, you're welcome to join us. Okay, and I hope you are learning something. Please, we're going to solve this particular question. If you've not screenshot what is on the board, please kindly do so, because I'm going to wipe the left-hand side of the board so I can be able to solve this question. Okay, let me wipe this, and then we solve the question and see. Solution. Now let's declare the data first. The charge, the value of the charge was given to us in 1.6 times 10 to the power of minus 19 coulomb. We are given the flux density, that's magnetic field strength, B, to be 10 Tesla. The unit Tesla, or Weber per square meter. Then the velocity of the charge was given to us to be 3 times 10 to the 7th power meter per second. The first part of the question, we have to calculate the force acting on the charge when the charge moves parallel to the field. When the charge moves parallel to the field, theta is equal to 0 degrees. Take note, theta equal to 0 degrees. In fact, I don't even need to solve anything in this first part of the question. The answer to that first part of the question is 0. I highlighted that, I explained that on this side of the board, I've wiped it. You know, condition for maximum force, condition for minimum force. So when the charge moves parallel to the field, there is no force acting on the charge, the force is equal to 0. The reason is because the angle is 0. That is the angle at which the charge is moving to the field. Okay, is 0 since they are parallel. And if you apply the formula F equal to QVB sin theta is 0, 0 times QVB is equal to 0. Anyway, just for the purpose of you saying F is equal to QVB sin theta, and of course this is going to be F equal to Q. If you want to substitute Q, the choice is yours. I am not interested in that. Since theta is 0, I want to fix sin 0, and then D is equal to 0. So there is no force acting on the charge in this case. In the second case, the charge is moving at right angle to the field. At right angle to the field means that theta is equal to 90 degrees. And of course, you know that under this condition, maximum force is experienced. And when maximum force is experienced, the force acting on the charge is equal to QVB, the charge times the velocity times the magnetic flux density. That is maximum force. If you want to use QVB sin theta, the choice is yours. In that case, sin theta is 90. Right angle means that theta is 90. Sin 90 is 1. I've already explained that concept. Therefore, I'll just simply want to use this QVB as the formula, no time to waste. And then we're now going to substitute. Our charge is equal to 1.6 times 10 to the power of minus 19 coulomb. We multiply by the velocity, which is 3 times 10 to the power of 7. And then we now multiply by 10, which is the value of the magnetic field strength, or the flux density as you might choose to call it. From here, the force acting on the charge will now be equal to, and that force will be maximum, you know. How do you work out this? Multiply 1.6 by 3. This is times 10 to the power of 19, this is times 10 to the power of 7, this is times 10 to the power of 1. You can use indices law, multiplication law of indices to handle all the terms. Pick one of the terms and add their powers. So let us focus on this 1.6 times 3. If you multiply 1.6 times 3, you will get 4.8. So this is going to be 4.8 multiplied by 10 to the power of. Now add power 19, minus 19 to 7 to 1, the powers of 10. Minus 19 plus 7 is going to give you what? Minus 19 plus 7 will give you minus 12, right? To give you what? Minus 12. Then minus 12 plus 1 would give you minus 11. So this is going to be minus 11 Newton. Minus 11 Newton. And this force value, the force acting on the charge in this case, is actually maximum force. It's maximum force since the charge is moving at right angles to the field. Yeah.